All right, let's continue our discussion of summation notation. So in the last video, we introduced summation notation, like what it means. And now in this video, we're going to talk about how to use summation notation. Now first, I just want to get used to using it with very simple examples. Or not super simple, but straightforward mostly. But then I want to run into examples that may make it a little more tougher, which we're going to have some properties, as you can see towards the bottom of the page, we'll have some properties that will allow us to work with tougher ones. Now, to start with, let's just look at a couple ones that actually work out, fairly easily. This first example A, we have the sum from I equals 1 to 5 of I. Now, let's think about evaluating that. That literally means plug in a 1, well, you just get 1. Plug in a 2, you get 2. Plug in a 3, you get 3. Then plug in a 4, then plug in a 5. And the sum, it means you add all those. So 1 plus 2, I guess that's 3, plus 3 is 6, plus 4 is 10, plus 5, so I guess you get 15. So that's the sum, I guess, of the first 5 positive integers. 15. That's easy enough. Okay, what B? We have the sum from n equals 0 to 4 of 2n plus 1. Okay, so we plug in a 0. What do we get? 2 times 0 plus 1, you get 1. Plus, plug in a 1. 2 times 1 is 2 plus 1, so I guess that's 2 times 1 is 2, that's 3. Plus, okay, so this is where we plugged in a n equals 0, n equal 1, plug in an n equal 2. Well, okay, that's 2 times 2 is 4 plus 1 is 5. So that was when n equals 2. Plus, okay, let's plug in an n equal 3. You plug in a 3, 2 times 3 is 6, plus 1, that's 7. Now you might notice a pattern here. It looks like these are all the odd integers. All right, plug in a 4. And we have 4 times 2 is 8 plus 1 is 9. Yeah, so 2n plus 1, that's a way to represent odd integers. And so if we add these up, we get 1 plus 3, I guess that's 4. Plus 5 is 9. We have another 9, that's 18. Plus 7, I guess that's 25 if I added those correctly. The sum of those odd integers, the first 5 odd integers, 9 plus 7, that's 16, plus 5 would be 21, plus 4 would be 25, yeah. Okay. What about C? It's the sum from j equals 2 to 7 of, 2j squared. Okay, so we plug in a 2 to start with. You get 2 times 2 squared. So 2 squared is 4 times 2, that's 8. So that's when we plugged in j equals 2. Plus, now let's plug in j equals 3. All right, plug in 3. Okay, 3 squared is 9. Times 2, that's 18. Plus, plug in j equals 4. 4 squared is 16 times 2 is 32. Plus, plug in j equals 5. 5 squared is 25 times 2 is 50. Plus, now plug in a j equals 6. Okay, 6 squared is 36 times 2 is 72. And then we stop at this last term where we get j equals 7. So 7 squared rather is 49 times 2 is 98. And now we just add up those terms. Here I'm going to make things go a little faster. I'll use my calculator. 18 plus 8 plus 18 plus 32 plus 50 plus 72 plus 98. We get 278. Okay, so again, the sum simply means to do all those terms individually and then add them up. Now D is a little interesting here. And I wanted to add this on purpose because Notice that there is another variable n here. And n is not the index. The index is k, which means you're plugging into the expression for k. Okay, so let's see how that affects this. So we're going to plug in, here, let's just say sum of k equals 3 to 8 of n times k cubed minus 1. Okay, so we plug in 3. You get 3 cubed is what? 27 minus 1 is 26. Then you get times n. So you get 26 n plus, okay, that was when you plugged in a 3. Oh, not n, okay, sorry. We don't know what n is. N is not specified. K equals 3. And then we plug in k equals 4. Okay, 4 cubed is 4 times 4 times 4 is 64. Minus 1 is 63 times n. 63 n. Plus, now plug in a 5. So k equals 5. 5 times 5 times 5, k cubed is 125. Minus 1 is 124. Times n is 124n. Plus, and plug in a 6. 6 cubed is 216. 6 times 6 times 6. 6 times 6 times 6. Yeah, 216. Minus 1 is 215. Times n gives you 215n. Plus, 7 times 7 times 7, 343. Yeah, 343 times n. So when you plug in k equals 7, you get 343n. And then the last one, 8 cubed. I do not remember 8 cubed. 512. I should know that. 512. Oh, you know what? I didn't subtract 1. That's 342n. 343 minus 1 is 342n. And then 512 would be 5. Minus 1 would be 511n. Ooh, almost. Good catch. That's k equals 8. Notice that each of those has an n in them because the expression does, and we're not indexing n. The index was k. Now, what does this give us here? Equals. Okay, we have basically they're all common terms because they all have an n in them. So 26 plus 63 plus 124 plus 215 plus 342 plus 511 gives us 1281n. Okay, so there we go. We're going to have a property that deals with that n here in just a few minutes. Example E. We have the sum from I equals 1 to 100 of I cubed. Okay. Plug it in 1, 1 cubed is 1. Plus, plug in a 2, 2 cubed is 8. Plus, plug in a 3, 3 cubed is 27. Plus, plug in a 4, 4 cubed is 64. Plug in a 5, 5 cubed is 125. Plus 6 cubed is 216. Plus 7 cubed is 343. Plus 8 cubed is 512. Plus ... I'm not doing this. That's the point of me. That's the point of me putting this in here. For us to realize there's no way that we're going to sit here and calculate the cube of the first 100 positive integers and then add those up. That's just a waste of our time. That's the point of me having that exercise in here. So what do? Okay, we need some ways to speed up these calculations. And theorem 4.41 is going to do it for us. So we're going to revisit example E here in just a sec. So let's look at these examples. Sorry, these properties. The first one, okay, first of all, let C be a constant. What does this first one say? This first one says if you have C times your an expression that's indexed, so C is a constant, you can factor it out and put it out front. Now that should make a whole lot of sense. Just because, hey, we had that same property with limits. We had that same property with derivatives. we have that same property with antiderivatives. And now we have that same property with summations. It's basically, like, we can call it the constant multiple rule for summations. Okay, now so that gives us another way to solve D. Here, I'll erase E since that's not going to be the way we solve that. Another way to solve D would be to say, hey, N is treated like a constant because it's not indexed. So we could say this is equal to N times the sum, K equal 3 to 8 of K cubed minus 1 equals N, and then we add up the 26 plus the 63 plus the 124 plus the 215 plus the 342 plus the 511, and we get N times that sum, which we found was 1281. So that's 1281 N. Okay? So we could factor out the N because it's not indexed. Anytime you have, even though it looks like a variable, N is usually a variable, but it's not indexed in this case because the only thing that's indexed are K's, not N's. So that's a helpful property. Okay, what does this next one say? Hey, that's another familiar property. What does it look like? That's a sum difference property. We had the same property for limits, for derivatives, for antiderivatives, and now for summations. It says if you have the sum of two different terms that are indexed, so the sum from I equal 1 to n that are indexed according to I, you can take their sums individually and then add them or subtract them, whatever is appropriate. Okay, this will be a big help for us. And now these last four are ways to evaluate sums quickly. Now notice that all four of these last four properties, all are indexed starting at 1. That's important. So for instance, these properties would not work for B, not work for C, and not work for D. The properties that have boxed off would not work because those are not indexed starting at 1. Now I suppose you could rewrite, if we really wanted to, we could like rewrite this theorem and have them indexed at 0 or 2 or 3, but that's more trouble than it's worth. So to use these four, they're called identities. They're called summation identities. To use these four summation identities, you have to have a summation that's indexed starting at 1. Kind of like example E above is. It starts at 1 and ends at 100. That fits the bill completely. So again, these are called summation identities. Okay, and then what does this say? This says if you have the sum of a constant, all you have to do is multiply the upper bound times the constant, and you're done. Easy. Now, why does that probably make sense? Because think about it. If you have the sum here, let's just do an easy one. If you have the sum of like I equals 1 to let's say 3 of 5, what it means is, all right, plug in a 1. Well, it's a constant, so you just get 5 out. Oh, equals, sorry. Equals. You plug in a 1, it's a constant, you just get a 5. Plus, plug in a 2, it's a constant, you still get a 5. Plug in a 3, it's a constant, you still get a 5. So 5 plus 5 plus 5 is 15. The summation identity says the sum from I equals 1 to 3 is of 5 is equal to 5 times 3, which is 15. Okay, because when you plug in and it's a constant function, you just get the constant back, and you get the constant back n times. So n times the constant gives you the answer. Okay. Now the others aren't so obvious. I mean, if basically if you ever take a class called number theory, you'll learn how to show those are true. Basically, it uses this process called mathematical induction, which is a very interesting process, but I won't bore you here. We covered extensively in my number theory class with which is like math majors take that. Okay, so it's very interesting to me, but it probably won't be very interesting for you. So these are not, the rest of these are not at all obvious, but they need to be memorized because these will be used a lot in this section and the next. This says the sum of the I squareds from 1 to n is n times n plus 1 times 2n plus 1 over 6. That just needs to be memorized. This one right here says the sum from I equals 1 to n is n times n plus 1 over 2. And the last one is talking about the cubes. This says the sum of the cubes from I equal 1 to n is n squared times n plus 1 squared over 4. I guess I will say this. We won't probably use this one as much. It'll be used in homework, but not. I probably won't give you a cubic one on a test. I'll probably stick to the others on a test. But so that's one you can kind of reference in your notes as you need. But for test purposes or exam, these for sure. You'll need to know those on a test. Okay, because those are going to allow us to use this thing that we're about to talk about called a Riemann sum to find the area bounded by a curve, 2 vertical lines, and the x-axis. So you'll need all those for sure. Okay. In the meantime, let's practice our summation notation a couple more times. Let's use these properties. So let's revisit that example E. And now we can solve it using these properties. So here's example E all over again. Obviously, we don't want to write out 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. But this is exactly what we're told we can do. This says the sum of the first n cubes is equal to n squared times n plus 1 squared, or 4. So this is a shortcut way to evaluate the sum. So the sum from I equals 1 to 100 of I cubed is simply n squared. So here's our n. That's the upper bound. So it's 100 squared times 100 plus 1 squared over 4. So what, 100 squared times 101 squared over 4? Which I have no idea what that is. Somebody use a calculator. 100 squared times 101 squared divided by 4. Whoa, that's a big number. Ooh, 25 million 550 million, sorry, 550,000. Or was that 2 million? Oh man. 25 million, no, 502,000. That's where I got messed up. 502,000. 500. To be honest with you, didn't expect a number that big. That's a big number. But I guess it makes sense, right? I mean, if you plug in think about the biggest number in that summation, 100 cubed is what? 100 cubed is a million? Yeah, is a million. So you're adding some really big numbers. So I guess that makes sense that you would get a really big number like 25 million. Okay? So obviously that's a way faster than doing 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. That would take you all day. Okay? The identity lets you do it in a few seconds. Well, B. Excuse me. B says we have the sum from I equals 1 to 50 of I squared plus 4. Okay, we have the sum of 2 terms. Okay, we have the sum of 2 terms. It's kind of weird. We'll say sum. We have the summation of the sum of 2 terms. So we can use the sum difference rule up here to take those summations individually. And we could say this is the summation from I equals 1 to 50 of I squared plus the summation from I equals 1 to 50 of 4. And now we can use identities to do the last bit of work for us. We have what? We have the first one's the sum of the I squareds. And the second one is the sum of a constant. So we can use these two identities. The sum of the constant, well, is, the I squareds first. You have a fraction over 6, and it's n, so again, n is the upper bound here. That's 50. So we have 50 times 50 plus 1 times 2 times 50 plus 1 over 6 for the first one. And the second one is a constant, so it's just 4 times the upper bound, 4 times 50. Now, again, at this point, this is just a job for your calculator. Let's see, 50 times 51 times, what's 2 times 50 is 100 times 1, so times 101. Divided by 6. For this first number, you get 42,925. Plus what's 4 times 50? That's what, 200? So it's 200, and you get 43,025. Okay. Ooh, what about C? C, we have 3 terms. Okay. C, we have 3 terms. So let's see what we can come up with here. So we can use the sum. By the way, just like with the sum difference rule for derivatives, for limits, and for antiderivatives, we write the theorem with 2 terms, but it applies to 3, to 4, to 5, to 100 terms. If you want to take the summation of a bunch of terms added and subtracted, you can take the summation the summation of each individually, whether it's 100 terms or 2 terms. So here we have 3. We have the sum and difference of 3 terms. We can do that each term individually. Now clearly it's the sum from I equal 1 to 200. You would not want to do this by hand. 50, I still don't want to do it by hand. It's much quicker not to. But I suppose conceivably you could. Now, here's the thing. Never fails. I give a test. It never fails that I'll give a problem like this. It'll be like the sum from 1 to 75. And somebody is going to take like a whole back piece of paper and write it all out and use their calculator to add them up the first 75 terms and waste 30 minutes doing it. Please don't do that. Memorize the identities to make this a 2-minute problem instead of a 30-minute problem if you're going to try to add all those terms. Okay, so let's look at what the identities can do for us. We can write these individually as the sum from I equals 1 to 200 of 2I squared minus the sum from I equal 1 to 200 of 3I plus the sum from I equal 1 to 200 of 4. Now for the first two, notice I have constants, a constant multiple for each. So what I can do for those is factor out the constant. So I have 2 times the sum from I equal 1 to 200 of I squared minus 3 times the sum from I equal 1 to 200 of I plus, and we can just leave that as a 4. I suppose you could factor out and get a 1 there, but that's not really advantageous since we already have a constant rule to deal with the sum of a constant. All right, so now we can use the identities. We have a 2 out front times, what's the sum of the I squareds from 1 to 200? Okay, so n is 200 here. So we're going to use this property now. Actually, we're going to use the I squared property first, and then the I identity, and then we're going to use the constant identity. Okay, so it's going to be the first one, n is 200 for all of them. So we have 200 times 200 plus 1 times 2 times 200 plus 1 all over 6 minus 3. Now this is the sum of the i's. So we're looking at that one. N times n plus 1 over 2. So 200, 200 plus 1 over 2. And for the last one, it's a constant. So we're looking at the summation of a constant. And we get plus 4 times 200. And again, drop your calculator at this point. So just be careful. Don't make any typos. I'll try my best here. We have 2 times 200 times 200 plus 1, so 201, plus 2 times 200 is 400 plus 1, so 401. So times 401, sorry. Almost made a mistake. Divided by 6. Minus 3 times 200 times 201 divided by 2 plus 4 times 200. Another very big number. This is 5,313,900. So I mean, you definitely don't want to be doing that one by hand either. 200 terms. You have to square and then subtract and add, the summations. While it takes 5 minutes, way quicker than the alternative. Okay, last example here, example D. What we have here, we have the sum from I equal 1 to 75, 3 times I minus 1 squared. Okay, this is going to take some algebra. Why? Because first of all, we have a 3 we can factor out. But then we have I minus 1 squared. We have no property up here that deals with basically a composite function. I minus 1 squared. We have the sum of the i's, the sum of the I cubes, sum of the I squareds, a constant, but not I minus 1 quantity squared. So we're going to have to use a little bit of algebra to rewrite that. So first off, let's apply the constant multiple rule and say this is 3 times the sum from I equal 1 to 75 of I minus 1 squared equals, okay, we have a 3 times the sum from I equal 1 to 75. Now what's I minus 1 squared? Now don't think imaginary numbers here. I is just an index, it's just a variable. Okay, so I squared is just I squared, not like -1 or anything. Probably should have mentioned that a little while ago because we've been dealing with I squareds. No imaginary numbers in this class. So if you FOIL this, you got I minus 1 times I minus 1. So you get I squared minus 2I plus 1. So I squared minus 2I plus 1. And now we're kind of like to the same spot in example C. We have 3 terms, except now we do have a 3 out front of all of them. But we can take those sums individually. We have the sum of I equals 1 to 75 of I squared minus the sum from I equal 1 to 75 of 2I plus the sum from I equal 1 to 75 of 1. Close parentheses, since that 3 applies to all of those sums. We gotta be careful in that regard. Equals, okay, I should probably take that constant multiple out, or we have to actually. And so we get the sum from I equal 1 to 75 of I squared, nothing changes there, minus 2 times the sum from I equal 1 to 75 of I, and then nothing changes on this last term, I equal 1 to 75 of 1. Equals 3, okay. Oh, we need to back up a little bit because we're going to need a little extra room here. Equals 3. Okay, what's the sum of the I squareds? I squareds are right here. Now 75 is the value of n, so we have 75 times what? 75 plus 1, 76, times 2 times 75, which is what, 150 plus 1, so 151 over 6. Minus 2 times the sum of the i's. Now where's the sum of the i's? It's right here. So 75 times n plus 1, 76 over 2. Plus, we have the sum from I equal 1 to 75. So that's using the constant summation rule, which says you take the constant 1, multiply by the upper bound 75, so plus 75. Oh, and at this point, just a job for your calculator. So I'll multiply by the 3 last. I'm going to do this stuff inside the parentheses first. 75 times 76 times 151 divided by 6 minus 2 times 75 times 76 divided by 2 plus 75. And then last we need to multiply by 3, and we get a fairly big number, 413,475. So, although those were not a piece of cake necessarily, they still took a little bit of work. Much, much, much faster than writing out 75 terms, or 200 terms, or 50 terms, or 100 terms, and adding up those. That would take us the entire day to do all that. And then we'd probably make a mistake on our calculator and get the wrong answer. Okay? So that's summation notation. And that is what we're going to use to solve, going back to where we started this in the last video. We're going to go back to writing out the product, the area of rectangles and adding up all those areas. We're going to write that using summation notation. That's the whole point of this little tangent off to the side, was to figure out how to take a big summation of areas of rectangles and write it in a very concise manner. And sigma notation was the key to that. So that's where we're headed next. We're going to go back to our rectangles, finding the area bounded by a curve, 2 vertical lines in the x-axis, and using rectangles to approximate that, and then using summation notation to write that in a concise manner and to evaluate those summations quickly, or relatively quickly. Okay, I'll catch you next video. Until next time, have a good one.